to reiterate, we are going to continue with the metric system. We're going to be measuring grams. We're going to use those balance scales. Some of you have done that before. But you need to understand the difference between weight and mass before you get into doing those measurements. This week, there is lots of hands-on stuff, and that is important to you because some of you love labs. I personally like labs because it means I don't have to sit and talk all period. But you need to be aware of the fact that you're going to have limited time when you do labs, just like in-class assignments. This last week, it was all homework with one in-class assignment. This week, all this black stuff is our labs. And if you don't learn the concepts that you have to apply when you get to the lab station, you're going to be struggling, and that's going to take time. And you just don't have the additional time. We're going to measure all these items you see up here tomorrow in the lab. Plenty of time if you cooperate, plenty of time if you have learned how to measure mass and you paid attention today. Not enough time if you think you're going to sit there and talk about, the movie you went to over the weekend or chit-chat about whatever. You need to stay on task or you won't get these things done in time, okay? Can't give you extra time. I can't say, well, here, go ahead and take all this stuff home. You've got to get it done in the allotted time, okay? The next thing I want to point out before we get into today's lecture is grading on the assignments. I looked at some of those grades that you guys assigned. They weren't accurate. Some of you marked things right that should have been marked wrong and vice versa. But the biggest thing that concerned me is some of you were under the impression that if a person left it blank, that it was okay. Okay? If you leave an answer blank, it's wrong. So you don't just grade it out of however many they did. Maybe you did that way back when in elementary school, maybe even last year, but in here, and when you take your Ames test, or you take any other test, a blank answer is no answer is wrong. So make sure you do fill them in. And if it's multiple choice or true false, don't ever, just leave them blank. I always give you a warning. You got 5 more minutes, you got 1 more minute. Circle it real quick if you have to. Get something down there. At least you got a shot at it. A 1 in 3 or 1 in 4 shot at getting them right. But don't leave them blank. And again, those of you grading them, you mark those ones wrong that were left blank. Okay? If I see a continued problem with how you're grading things, either you have to decide, hey, I can't do this, and turn the paper into me and let me grade it, or you're just being dishonest at that point. Okay? And the point's going to come off of your grade because you're clearly not following the rules. Any questions on that? All right. So we're back to the question of mass versus weight. And I did a little demo for you on Friday. I showed you my weight loss plan. How many of you thought I really lost weight if I was falling through the air? Okay? Those of you that think that I did in fact really lose weight, you're wrong. I did lose weight. But it isn't weight the way you guys think it is. You go on a weight loss plan to look better. It is true that as I was falling through the air, that fat did not come flying off my body. Okay? I was the same person standing up on the table as I was in the air as I was on the ground. My weight changed, but my mass did not. Can someone give me a definition for mass? Now, we talked a little bit about this on Friday. It's mass area. I appreciate you going out there on the limb and taking a shot. That's not the answer I was looking for, though. There, now we're getting somewhere. When we talk about mass in science, we're talking about what's actually in that object. What kind of matter, how much matter is in there. It's not about how big something is. Head up, please. Let's not fight this battle over today, all right? The word massive. The hot air balloon was massive. The linebacker was massive. You think of massive means big. Okay? That's not what it means in science. How loud the stereo is volume. Okay? You say the volume was set up really high. I say the amplitude was set high because I'm a science teacher. I use science words. In science, volume is not about how loud something is. It is about the amount of space it takes up. Showed this to you on Friday as well. I said that this is 1 liter of volume. A liter of volume is the amount of space it takes up. Not the type of liquid, not how heavy it is, none of that matters. Just the the amount of space. When I measure the amount of space, I'm using volume. Mass is not about the amount of space. You're right. It has something to do with the kind of matter and how much is in there. So we're going to get a definition of weight today. We're going to get a definition of mass and a couple other things. Can someone give me a definition for weight? Let's start with that one. What do you think it is? It's a simple one. Weight is, who said that? No, that wasn't that hard. That's what you were going to say, right? Probably. I know, but I still will call on people even if they aren't very familiar. Okay, weight is about how heavy something is. So, what creates the weight of an object? What makes an object heavier? Gravity, and what else? There's two things that go into an object's weight. Gravity and mass. Mass, you're absolutely right. So, if you thought that these two words were related, you're right. Mass and weight do have something in common, but they are not the same thing. We look at these three situations. Here's this guy on Earth. Here he is in orbit. Here he is on the moon. Three different situations. We can measure his weight, we can measure his mass. If his weight is 60 kilograms here on Earth, what do you predict? I'm not saying this is right, but what do you predict right now his weight will be in orbit? 0 kilograms. Does anyone disagree with that? Does anyone else in this class have an opinion? No. Okay, how about on the moon? What's his weight going to be on the moon? Okay, where did you get that number? Why 12? I'll give you a little hint here. The moon has 1/6 the mass of the Earth. Want to change your answer? 12's not far off. What do you think? 10? Okay. Or 10 kilograms would be his weight on the moon. Now predict, if his mass is 60 kilograms on Earth, what do you think his mass will be in orbit? Yeah. What will be his mass on the moon? 60 kilograms. Alright, well I'll just tell you guys right off the bat that all your answers are right. But sometimes you need the right answer, isn't the goal. The goal here is to know why. Why is it that in all three situations the mass stays the same? Anyone know? Okay, now remember, mass isn't about how big you are. His matter doesn't change. Same dude, wearing the same goofy clothes in all three situations. His matter doesn't change. So his mass is the same. Why is it that his weight does change? It's different in all three cases. Gravity, excellent. Now we're on the right track here. So now that you understand that, let's look at gravity. And let's look at weight. Here's the definition for weight. All you need to do is get this top part down. Weight is determined by the effects of gravity on mass. The effects of gravity on mass. Now, at the bottom, I kind of try to explain that to you. If I were to ask you later, what two things determine weight, your answer would be gravity and mass. We haven't talked a lot about mass. You did kind of mention it already. Nathan said something about the type of matter, and he's right on track in describing mass. It does have something to do with the type of matter and some other things as well. But think about the stuff that goes into it. The mass of meat, the mass of that cup of water didn't change. When it was falling through the air, it was still a cup of water. When it landed in the bottom, it was still a cup of water. It never changed. And with weight, because it's dependent not just on mass, but gravity, gravity does change. Gravity has a lot to do with gravity of whatever you're next to, such as the Earth. But it also has a lot to do with what you're doing. Right up against this. It says the greater the mass, the greater the weight. However, while the amount of gravity changes throughout the universe, mass remains constant. just like we saw in those three examples. Gravity is different on the Earth than it is on the moon, so he weighs less. But his mass was still the same. Mass is not affected by gravity. Mass stays the same. It's about the type of material. So let's look at gravity. It says, gravity is created by all objects with mass. This is the definition of gravity. The greater the mass, the greater the gravity. Now, I don't think I need to tell you to write down that gravity is the pull or the attraction to the object. I think you know that part. I know it doesn't show up anywhere. Gravity is created by all objects with mass. The greater the mass, the greater the gravity. Even you have a gravitational pull, it says, but it's small compared to the Earth's gravity. All objects with mass have gravity. Gravity is the attraction that's going to pull things towards it. Gravity is one of the basic forces in the universe. So if you have gravity, why is it that when I drop this pin, it doesn't come shooting towards you? Why does it go towards the center of the Earth? And why does the Earth have more gravity? It has more mass. Why does the moon have less gravity? Because it has less mass. Again, mass is not about how big something is. It's about how much stuff is in there. And yes, the moon is smaller and it also has less stuff. Happens to be 1/6 as much stuff as the Earth. So it has 1/6 the gravity. So that little girl that weighs 60 kilograms on the Earth would weigh how much on the moon? 10, just like the prediction on the other page. You were right. Gravity is one of those things that a lot of people don't understand. I mean, it's around us all the time, but you don't understand how it's working. It has to do with the object that you're next to. In this case, the strongest gravity that we're next to is the Earth. If we weren't around the Earth, if we were away from any other forms of gravity, out there floating in space, could be little particles would start to gather around you, would start to orbit you. And maybe they would combine together and make little teeny tiny planets. And all those little planets would be little life forms that would think that you're the center of the universe. You're the sun. Okay? But maybe you are. You're the most massive thing around. But here on Earth, your mass is nothing compared to the Earth. So the effect of gravity that you create is very small. Now, what is the biggest thing in our solar system? The most massive thing in our solar system? The sun. And I want to correct myself because I said biggest thing. I don't like to use the word big. I want to use the word massive because that's talking about the amount of stuff that's in it. So the sun has a lot more stuff. You can see the outline of the sun over there, how big that would be compared to the Earth. And the Earth is not even, that size is not even accurate. It's a little white dot in there. So a little thing like this compared to this huge thing. So if the sun has a lot more mass, it has a lot more gravity, why aren't, when we drop things here, why aren't they just pulled towards the sun? Too far away. Close enough, strong enough to hold us in orbit, but compared to the Earth's gravity, we're going to feel the Earth's gravity a lot more. What keeps the moon in orbit? Okay, but what keeps it there? The Earth, does the Earth's gravity keep it there? Keep it from getting away? Yeah, you're right. It's at that perfect little spot. If it got farther away, it might escape our gravity and be pulled in by something else, but it's just close enough that we hang on to it. Like a string, like a ball on the end of a string that you're spinning around like this. Just strong enough to hang on. Yes. No, right here in front. What do you mean, close to the sun? Well, the sun's not orbiting around the planets. You do understand that, right? The sun is, in fact, orbiting around a central mass within our galaxy. So even in our galaxy, we have the Milky Way, you've heard of that, right? And it's got these arms that curl out like this. That whole thing is rotating around. And we're about 2/3 of the way out on one of those arms, sitting there, okay? And we're staying there because of where most of the mass is. Most of the mass in our galaxy is in the center. And we're held in, just like the moon is held in its orbit, our solar system is held in orbit by the mass of the entire universe, the entire galaxy. So all these things are kind of held in these little places in space because of gravity. Nathan?
Yeah, why does the moon and the Earth both have those gravity together?
Because there's countering forces. You know, when this object goes around, it's pulled away, called centrifugal force. And then there's this force that pulls it in, called centripetal force. And the forces are equal and opposite right now. If we throw that force out of whack a little bit, it will either escape or it will come crashing into the Earth. Okay? And that has been known to happen. Satellites of some other planets in our solar system have knocked into others and into the planets and knocked off pieces. Hopefully it won't happen in our lifetime. Good questions, though. Both good questions. So gravity. Got a sense of gravity. Now, what a lot of people don't understand about gravity is that it's not just the Earth has this force that pulls things, pulls the moon. And the moon has its force that pulls things. And the sun has its force. Gravity also has to do with what you're doing. If you're moving, you can affect gravity. You can make it stronger. You can make it weaker. And when you ask a kid in elementary school, or maybe you can try asking your parents this question, ask them, why is it that an astronaut in orbit is weightless? Try it out. They'll probably get obnoxious and say, I already graduated, kid. I'm not answering that question. A lot of people don't. There's a lot of misunderstandings out there about gravity and weightlessness. And in fact, I want you to help me come up with some of those goofy reasons that you know aren't right, or maybe you think are right, but you're not sure, for why the astronaut would be weightless. What do you think causes weightlessness? Let's scratch your gum. Which one? You're chewing on something, man. Salt. Too far away. That's a common one. What else? What else do you think people say? What has magically changed from being down here on Earth to being out in space that makes gravity no longer seem to have an effect? Okay, there is no gravity. But why? What is different about space that would make there be no gravity? Okay, that's a common one. No air, no atmosphere. Any others? Yeah, that's a common one too. Not touching the ground. Now, hopefully, you can all identify these as incorrect. It doesn't make sense. But if not, you should be able to reason it out. Let's take each one of these. Let's start with this one, not touching the ground. If that were accurate, every time you flew on a plane, you would suddenly become weightless, right? You're not touching the ground there. Or, if I jump up in the air, I'm no longer touching the ground, I would be weightless. That's not how it works. You don't stay weightless. Gravity pulls you right back down. Air. This is a big one. A lot of people confuse gravity with the atmosphere. Surrounding the Earth is this very thin layer separating us between life and death. And we have to escape that to get out into the vacuum of space, we call it, where there is no air. Now, if I take air away, do you suddenly become weightless? If I put you in a room and I suck out all the air, are you now going to float? You will die in short order, but you will float. Okay? The air is not what gives you gravity. Two totally separate things. And then we get to this part. You're too far away or there's no gravity. Well, let's think about it. What keeps the moon in orbit around the Earth? The Earth's gravity. So you're telling me that the Earth can pull on the moon enough to hold it in orbit, but it won't have any effect on the astronauts? Does that make sense? Can't be that. So what must be the answer? Why is it that you wait? You're right, the business of being in orbit is the important part. But what about the orbit? What is actually happening? I'll give you a clue. It's the same way I was waiting. You're falling. See, this is where it's kind of hard to understand. It's kind of like when you were a little kid. You said, if I take a hole, I'm going to wind up in China. Okay? Well, that might be. If you could dig it deep enough, you wind up on the other side of the Earth. But then you probably ask this question. How is it, if I'm over here on this side of the Earth, the people on this side of the Earth don't fall off, right? Ever asked that one when you were a little kid? Earth is a ball, because you're not thinking that gravity is pulling in all directions, from all sides, towards the center. So down is not always the same direction, right? Down for these people is a different direction than these people. See what I'm saying? So when you think of falling, you're always thinking from your point of view. Falling means going towards the Earth. What if, just before you reach the Earth, I pulled it out from underneath you? You keep falling, right? Well, that's precisely what's happening when you're in orbit. An orbit is a free fall, but in a circle. You see, you're so far away that when you fall, instead of landing on the Earth, you land away. You don't land. You just keep circling. So this is falling in a circle, believe it or not. You want to know what it's like to feel the weightlessness of space? You don't have to spend your whole life training to be an astronaut. Go on a roller coaster ride. Jump off your roof. But anytime you feel yourself free fall, that's the same feeling. Just imagine it constant. When they're up there, that's the feeling they get. It's this constant feeling of falling. Now I'm sure after the first hour or two, their brain kind of gets used to it. But that's what they're going to feel, you know, when your stomach comes up in your throat, that kind of thing. If you watch a video, you see the astronauts before they get on the space shuttle, and then you see them up in space, you got puffy cheeks. They often have a stuffy nose, because all the fluids in their lower body get pulled up into their head and neck and shoulders, and so they get really puffy up there. Because it's just like they're falling. Okay? So you're falling in a circle. Let me just show you how that works in an orbit. So the way that space shuttle is able to maintain that constant fall is it creates an orbit. It gets up high enough, and then it fires its engines so that it can go around the Earth without falling into it. Okay? And that creates what we call a stable orbit. Like if I'm up the top of a very, very tall building, one that's way up there, and I throw the ball, it's going to fall down and hit the Earth. Big shocker, okay? Even if I'm outside the atmosphere, outside and there's no air, it's going to fall towards the Earth. Gravity's going to pull it down. But if I give it a little bit more oomph, and throw it a little bit harder, it'll fall in a different spot on the Earth. It gets farther, almost on its way to making it around. Not yet, though. Give it enough thrust, enough force, and now I put it into orbit. And it can maintain that indefinitely. We'll just keep going around and around in that orbit. Okay? Balance forces like we talked about with the moon. Just keep circling and circling. Okay? So that's what the space shuttle does. It gets up there, blasts off, and then it reaches an altitude, and then it fires its engine so that it can maintain this orbit. All they got to do is then point down a little bit and fire their engines so they angle down until finally they come around and land. See how that works? Okay? So gravity. Now the interesting thing about gravity is that you can make it stronger or weaker based on what you are doing. If you are falling, you're going with the force of gravity. Let me demonstrate. I will be the force of gravity. Okay? You'll be the falling person. I'm going to punch you in the face, right? And just like in the Matrix, you know when they do this business, fall backwards, okay? You're going to move your head away at the same speed as my punch. Get it? Like this. Are you going to feel the effect of that punch? No, because you're moving with it at the same speed. So she feels nothing. That's like falling and being weightless. Okay? That's like on the roller coaster ride when you take the big drop and you go with the force of gravity. You want me to sing you a lullaby? Do you see how why I don't allow this? That's exactly what happens. I'm sorry I can't be more interested. But the opposite also happens during takeoff. You know, you're strapped into the rocket and 3, 2, 1. You've got gravity trying to force you down. You're going up at a great speed. You're fighting against gravity. You're going to really feel the effects. So now, you go to the back of the room, and you take a running start. And you run at me as fast as you can. And just when you get up to this point, I'm then going to punch. See the difference? It's going to get much more impact. And now she's going this way, and I'm going that way. Sit up. So that's what happens when you during takeoff. And we say you experience more G's. Have you heard that before? What does G stand for? G-force. G stands for the force of gravity. How many G's are you experiencing right now? 1. How many G's do you experience on some carnival rides that spin you around? Well, if you're falling, maybe 0. But the ones that spin you around real fast? Or go real fast? No, 1 would be what you're experiencing right now. 4, 5, and 6. Some of those carnival rides you guys have been on have allowed you to experience the same kind of G-forces that an astronaut experiences. Let me give you an example. You know that one that spins around really fast like this? Yeah, or you stick on the wall. Have you been on one of those rides where you get off and you're like crying? You have tears coming out of your eyes, but you weren't crying? Okay? It was the G-force, the force of gravity, 5 or 6 times what it normally is, was pulling the tears out of your eyes. If you've been on those rides and you haven't been able to pull your head away from the cushion behind you, okay? That's because your head suddenly weighs 5 or 6 times what it normally does. It normally weighs about 10 pounds, now it weighs 50 or 60 pounds. It's going to be hard to pull it away. You see what I mean? So we can make gravity stronger or weaker depending upon our motion. If we're falling, we make it weaker. If we're falling fast enough, it's 0. If we're going against it, we make it stronger. Pilots, not even out in space, wear flight suits. They press on their lower body so that when they do this, and all the blood that would be in their head and in their brain gets pulled out to go to their legs, they would pass out. But the flight suit keeps pressure on their legs so that blood stays in the upper body and keeps them from passing out. Lots of important things about gravity. Okay. So let's move on now and let's look at mass. I asked you to get your planner. Open it up to page 139. What is this called? What's this thing called? Right there. Periodic table of elements. You're going to use this more at the end of the year when we get to chemistry. I have one up there. Think of this right now as all the ingredients for everything in the universe. You want to make a batch of human, you've got all the ingredients you need right here. You want to make a dog, you can make that here. You want to make, gold, you got what you need, a single ingredient right here. What I'd like you to do right now is locate the element hydrogen. Locate the element gold. What's the abbreviation for gold? AU, right here. Notice that in the upper left-hand corner, we have a number, the atomic number. Hydrogen is 1, gold is 79. In the upper right-hand corner, we have what's called the atomic weight. Good. This one doesn't have it, yours does. The atomic weight. In fact, if you look at the atomic weight here, you can see that they do definitely go up as we go from this corner down to this corner. They get bigger and bigger. What that's telling you guys is that there's a lot more stuff packed into every atom, every particle of gold than there is to every particle of hydrogen. You look at this example here. Gold has a lot of these little protons, head up please, neutrons and electrons, whereas hydrogen has almost none by comparison, has just a few. So that means that if there's more matter in gold than there is hydrogen, there's going to be more mass. So if something is made of gold, it's going to have more mass than something made of hydrogen. Makes sense? Okay? Called the atomic weight or the atomic mass. So if you look at those numbers, you can answer some questions. Let's see if you caught on that. Let's say that I have one atom of hydrogen and one atom of gold. Which has more mass? Okay, pretty obvious. Let's say I have 200 atoms of hydrogen over here, a gas, which here in our atmosphere floats. 200 atoms of hydrogen, and over here, 1 atom of gold. Which one has more mass? The hydrogen. Okay? Mass isn't about whether things float. A metal plane flies in the air. It's got a lot of mass. Good luck trying to lift one of those. Okay? It isn't about that. It's about the number and type of particles. That's your definition for mass. Mass is determined by the number and type of particles found in matter. An atom of gold has gold atoms, has more particles in each gold atom than an atom of hydrogen. But if I get enough of those, I can have more matter, more mass, more stuff than than gold. Determined by the number and type of particles in matter. Okay, let me try a few more here and see if you can answer these. It's getting a little bit trickier. Let's say I have, look in the upper left-hand corner, I have 2 atoms of lithium and 1 atom of magnesium. Which has more mass? 2 atoms of lithium or 1 atom of magnesium. Thought I heard someone say it. Magnesium. If you don't know how she figured that out, 2 atoms of lithium, that'd be 2 times, well, basically 7, 6.94. Compare that, 14, to 1 atom of magnesium at 24. Well, you're going to have more stuff in 1 atom of magnesium. So it's not enough just to know the type of matter. Yes, a gold atom is always going to have more mass than a hydrogen atom. You also have to know how many of each of these you've got. Okay? So if I were to suddenly, replace my hand with one made of lead, that lead hand is the exact same size and shape as this one, but in every lead atom, I've got a lot more stuff packed into it. You see what I mean? So what would happen to my mass? It would go up. Okay? So you have to know the number and type. The cool thing about mass measurements is when you do them, they are one clue about the kind of material. Whereas weight doesn't answer that question. Weight just tells me about the effect of gravity on that mass. Again, same thing. This has got a lot more stuff packed into it than the hydrogen does. Alright, now we're going to get to the how-tos of measuring. Some of you know how to do this, so just play along right now. If you don't, you want to listen carefully, because if you don't get this right, you're going to get all the answers wrong tomorrow. When we measure weight, we use a thing like this, a scale. And I like you to avoid using the word scale to refer to these, because they work differently. A scale like this is going to use my mass and gravity pushing down to make the dial go around. Okay? It's going to measure the effect of gravity. If I take this out in space and I'm falling, I'm in orbit, I'm going to get 0. I take it to the moon, I'm going to get a smaller number than here on Earth. Head up. So that number will change. This guy, I can measure whether I'm here on Earth, whether I'm on the space station orbiting the Earth, or I'm on the moon. And I'll get the same reading no matter what. Now, how many of you have used one of these before? This is called a dual can balance. Okay, this works on the same principle as this one. It works by making comparisons. the first thing we do is we want to make sure that it's all zeroed out, it's all balanced out. That little arrow is pointing right in the middle. So we adjust the knob until it's all balanced out. Then we take the object we want to find the mass of, and put it in one pan, and we use these little weights that have already been measured. This is 100 grams. If I put that in there and it balances out, great. I know the answer. This is 100 grams. And here's the reason why you get you get the same answer everywhere with this one. If I go to space, what's the weight of this going to be in space as it falls? 0. What's the weight of this going to be? 0. You think 0 and 0 will still balance out? Yes, they will. Okay? If I go to the moon, this is going to be 1/6 what it was. This is going to be 1/6 what it was. Head up. Is it going to balance out? Yeah. Because with a balance scale, not just the regular scale over there, the balance scale, we're always comparing it to something that doesn't change. The mass of this hasn't changed, and the mass of this hasn't changed. So it will be the same on the moon, it will be the same in space, it will always balance out, just like you see here. If you use a bathroom scale, you use something that measures gravity and how gravity is pushing you down, you're going to get different answers. Even here on Earth, you might weigh slightly less, very little bit, but slightly less on top of Mount Everest. You're going to get a different measurement than you will down at the bottom of Death Valley. So your altitude, how far away you are from the Earth, will have a little tiny effect on the gravity. So you get way far out, then it'll have a bigger effect. But with a balance scale, doesn't matter, because whatever gravity is changing, it's going to change for both, and we'll get the same reading. All right. So with this guy here, this is going to work on the same principle, but instead of having two pans, it's like a teeter-totter. This is the center of my teeter-totter. This is the one seat, and this is the other kid that sits on the other end. It's actually 3 kids. We have a big, medium, and small kid. And they slide on these rails called beams. That's why it's called a triple beam balance. And you move them farther away to balance out a heavier thing. The first thing you want to do with your triple beam balance is make sure that these 3 weights, called riders or poise, move those weights all the way to the left. Notice that the one here in the middle, the heaviest one, always slides into notches. So it should never be in a position in between. It should always be on one of those 3 notches. Again, if you don't know what I'm talking about, I'm referring to this beam right here. It's either going to be 0, 100, 200, but it shouldn't be here in the middle. Because then we don't know what that measurement is. If I'm using the back one, same deal, except now it slides and locks in every 10 grams. We're measuring in grams. You can set it right on here, OG. And the third one, that one can slide anywhere along that rail. And there are little markings so you know what it is. So we want to make sure all 3 of those are all the way back. Then the next thing is, like I should have done on the pan balance, we're going to zero it out. Make sure that it's right at 0. When I do that, I should get myself down at eye level with this little white line of the 0. Again, I'm referring to this part right here. I want to get myself down at eye level. When you're cooking and you're measuring out, 3/4 of a cup, you put it in there. You don't put it on the counter and look at it that way and go, well, that's 3/4 of a cup. You hold it up so you can see through the side of the measuring cup, or you can tell if it's lined up to the top of the cup the way it's supposed to be. If you don't do that, if you try to take your measurements, your readings from an angle, you will be inaccurate. This is a phenomenon called parallax view. Let me show you what I mean. If I'm trying to read that clock, and I get down really, really low, I make the minute hand line up with a mark behind it that it really isn't lined up with. I want to read that clock from eye level, straight on. Maybe you've been with your mom or dad driving and you say, Mom, speed up, you're going too slow. Head up, please. You're going too slow. The speed limit's 45 and you're only going 40 here. And then she argues with you and says, no, I was going 45. You can't read the speedometer from where you're sitting. And she's right. If it's the old-fashioned kind with a needle, okay, it's going like this, she's sitting right in front of it. You're all the way over here. You're going to look at that needle and you're going to compare it to the numbers in the background. And you're going to see her speed as a lot lower than it really is. So again, it's important that when you're taking your measurements and calibrating it, like I am right now, that you get down there at eye level, lined up with it. So that means you're going to have to bend your knees, get down here like this, and look at that line, okay? If you turn the knob so that you turn the top towards you, the top of the knob towards you, that will make this beam go down. The way is up. If you try to do that, the thing just kind of bangs up and down. So what I recommend you do is take your thumb, put it on this so you can keep it from moving, turn the knob a little bit, and see what you get. Not enough, I still need it to go down. Turn it another quarter turn. Not enough. Just do little turns at a time. If you do a whole bunch, you're going to screw yourself up. And I'm almost there. But again, the point of my thumb over here on the right-hand side is so that it doesn't take so much time for it to settle after I've made my adjustment. Once you've got it adjusted, you've got it calibrated, then you're ready to take your measurement. You pick an item and you put it on the pan. It doesn't matter if it overhangs like this hammer. If it's a ball that wants to roll around, just find a spot, a flat spot where it will sit and not roll. But the first thing you do, calibrate it. Again, making sure that all three of these riders are all the way to the left. Take your object and put it on the pan. Which of these are we going to move first? The big, medium, or small? Typically you start with the big one and then you work your way down from there. If you know it's going to be something super light, you might start with the little one and work your way up. But if it's heavier objects, I'd start with the big one and work my way down. So I'm going to use the little one here first. Then let's try 100. 100 was not enough. So I move it to 200. 300. 300 was too much. Now it's down below. What do? Back to 200. Then what? I go to the top one. This is the medium-sized one. I go 10. Not enough. 20, 30, 40, 50. 50 is a bit too much. Back to 40. Now here it's valuable if you look at this scale. Look at what these go up by. Is it by ones? No. I mean, when it's actually written on here. It's actually written on here. The numbers are 2. So it goes 2, 4, 6, 8, 10. So line halfway between is obviously right here. This is 2, this is 0, this must be 1. And then the little lines in between, you got to look and see what they're with. So I'm going to move this little one slowly, and you can see here, zoomed in now, until I get it balanced out. Pretty close, there we are. Now, look at what that is. 6 is the long line. This is 5 right here. So what am I? What are each of these little lines worth? Not 2, but 0.2. If this is 5, guys, and this is 6, this is 5.2, 5.4, 5.6. So then what is my measurement of this object? 245.6. Exactly. What a lot of people do is they forget to read off of all 3 riders. They go, oh, it's 200 or 240, and they forget this one. Or they forget that the little teeny tiny lines are 0.2. They're not full grams. The big ones, 1, 2, 3, 4, those are full grams. Okay? Be real careful when you do that. Do I need to do another example, or do you have it? How many think you understand this already? Maybe just another example. All right, I will move on then. I'm going to give you the lab sheet. I'm also going to give you a lab number. So as soon as you get this, get your name, period, and date at the top, and then I'll go around and assign you a lab station.